Today we will complete SN1, SN2, all kind of substitution reaction in alkyl halide chapter.
Awesome.
Substitution reaction. Okay. So nucleophilic substitution is basically occurs via two pathways. Mainly it occurs via two pathways, SN1 and SN2. Two pathways are there. So like what do we mean by substitution? You can see, suppose we are having an alkyl halide CS3Br, and we have to do the substitution. Suppose we are having a simple thing, alkyl group is there, and then some living group is there. So a living group is the one like which is kind of more electronegative or bigger size atom, like chlorine, bromine, iodine, or we can say a group on which the negative charge can become stable, right? So that is a good living group. So substitution, what group can substitute this? Basically this carbon is having partial positive charge, this is having partial negative charge. So on the carbon, nucleophile can attack, right? The nucleophile,
Yes,
which is electron rich, that can attack and remove this thing, remove the living group. So finally you will be getting R and the bond with the nucleophile, and this living group is removed. Okay, fine.
Okay.
So now this thing can occur via two pathways. You can see, suppose if we have to remove this thing and we have to add this nucleophile on this carbon. So what we can do, we can think like normal person can think like that first case can happen when this group leaves first. This group leaves first and then the nucleophile attacks. Okay, this group
Yes.
leaves first and then the nucleophile attack. That is the one pathway. Second pathway, first the nucleophile attacks, then the living group removes. This is the second pathway. Only these two cases are possible, right? So
Yes.
basically these two cases are these two mechanisms, right? We are having two mechanisms, SN1 and SN2.
Yes.
In SN1 what happens? First living group removes or leaves from the reactant. Here in SN2 what happened? First nucleophile attacks. So first nucleophile attacks. So beta, like if we are clear in this thing that this will happen in SN1 and this is SN2. So why these names are coming, that I will explain. SN1, SN2. SN means nucleophilic substitution. What is the meaning of this 1 and 2? These 1 and 2 are basically order of the reaction, right? First order,
Yes.
second order reaction, like that. So when living group remove first, so now what kind of in what way the reaction will happen? Let us see. Suppose I am having carbon, and this is a carbon, and this is the Br I am having, and then I am having suppose ROH, or let us take CS3OH as the nucleophile, and yes, it is a nucleophile because oxygen is having lone pair of electron. What will happen? This lone pair will attack here. No, before attacking, actually the living group will remove, right? This is the case of SN1.
Yes.
So when the living group removes, you will be having a positive charge here and Br minus, like that. Now what will happen? This CS3OH, this will attack. Now this will attack on this carbocation, and carbocation means a p orbital, right? P orbital, vacant.
Yes.
P orbital. So basically the nucleophile is donating its electron to the vacant p orbital, and it can attack. Suppose the p orbital looks like that, so it can attack from here also, it can attack from here also. So either the this nucleophile can attack from the above and can attack from the below also, because the p orbital is having two lobes. Okay, fine. So we will be having finally CS3, 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 and this is OCS3, because that was the nucleophile, and the Br minus is removed. So you can
Yes.
see the reaction has happened in two steps. This was step number 1. This was step number 2, right? So step 1 means, just in step 1 you can see there is a formation of carbocation. In step 2, the nucleophile is attacking, right? In step 2, what is
Yes.
happening? The nucleophile is attacking. Okay, so this was having lone pair. Yes, so this was the mechanism in the case of SN1. So as the carbocation is forming, carbocation form हो रहा है, so we can say what could be the favorable reactant for SN1? What could be the favorable or favorite reactant so that the reaction proceed via SN1 mechanism? So the reactant can be the one on which the carbocation can become stable, right? Because you can see,
Yes.
if the leaving group removes first, so this can only happen when there is a positive charge becoming is the more stable one. The positive charge forms and that forms the more stable one. Only then it can happen that the leaving group removes first. Okay, so among 3
Okay.
degree, 2 degree and 1 degree, on which carbon we can say the carbocation is more stable? So we can say on the 3 degree one, right? Because 3 degree
Yes.
carbon will be having plus I from 3 sides. That is why it is having this is the rate or rate order for the SN1, right? For SN1, if you are having 3 degree carbon, then the rate will be faster. Okay, and rate of reaction is directly proportional to the slowest step. And which is the slow step? The one in which the carbocation is forming. So carbocation is forming in this step. So in this step, as the carbocation is forming, so this is the slow step. And in the slow step, there is no role of the nucleophile. Only this is the one which is breaking its bond, right? Nucleophile is attacking in the second step. So we can say in the slow step, there is only reactant is coming. And what is the reactant? Reactant is alkyl halide. So alkyl halide is only coming in the rate of the reaction. So what is the power of this one? That is why we can say that it is first order reaction or unimolecular.
Yes.
Unimolecular nucleophilic substitution. That is the complete name of SN1 mechanism. Okay, so yes,
Yes.
this is the thing. Now, now let us see some the mechanism in SN2, how the SN2 occurs. So in the case of SN2, suppose you are having CH3 and Br you are having, and then there is a nucleophile. Let us take OH minus, and then what this happens. So in this case, you can see in SN2, first the nucleophile is attacking. So if the nucleophile is attacking, then the leaving group is removing. First the nucleophile attacks. So the nucleophile is attacking because the leaving group cannot be removed. If the leaving group removes, the forming positive is not stable here. Why? Because see, if the leaving group removal was easy, when it is easy, it is easy only in that case when the forming carbocation is stable. But suppose the reactant is like that. If the reactant is like that, then the forming carbocation is not stable here. So this cannot be removed. But substitution we have to do. So for doing the substitution, we have only choice that the nucleophile attacks first and then the Br removes. So how it is becoming easy when the nucleophile is attacking on this particular carbon? Because it is attacking on the anti-bonding orbital of the CBr bond. See, whenever a bond is there, sigma bond is there, so there is an anti-bonding is also there, right? From the molecular orbital theory, we see this thing when two atomic orbital combines, so there is the formation of bonding and anti-bonding molecular orbital. So when a bond is formed, then there must be anti-bonding also. In respect to that bond, there is anti-bonding also. And anti-bonding is always opposite to the bond, right? Anti-bonding lobe is always opposite to the bonding. So if CBr bond is like that, then its anti-bonding is like that, just opposite. Okay, so now if the nucleophile is attacking here, so what happens when electrons are coming in the anti-bonding? Because nucleophile will be donating the electron.
Yes.
So if the nucleophile is donating its electron to the anti-bonding, so electrons will come here. Now this bond will starts to break, right? Because in a bond only two electrons can be there. So if electrons are coming here, so electrons, the bond will starts to break, right? So here we will be having a transition state. And how does the transition states look like? Transition states look like this.
Yes.
Br and OH. The OH is donating its electron to the anti-bonding, and the bonding is weak, becoming weak, right? And then what happens? Then after that, what will happen? This Br bond will break, right? Because this bond has completely formed now. So CH, this is OH, this is hydrogen,
Yes.
this is hydrogen, and this is the Br minus. So this is a one-step process, because whatever you are having now, this is the transition state. This is not the intermediate. What do you mean by transition state? The state in which bond formation and bond breaking both are taking place simultaneously. So yes, it is the case. Bond forming and bond breaking both are taking place. So here we can say the transition state we are having. So this is a step one process. Unlike SN1, SN1 was two-step process. First step was the formation of carbocation. Second step was the formation of product. But here it is happening in one step only. This transition state will be just, it is not intermediate. Like the graph will be like that. Like that. This is the transition state.
Yes. Okay.
Okay. Yes. So here, as there is only one step, so this is the one step which is slow step, and rate depends on the slow step. So rate is directly proportional to. In the slow step, what are the things coming? Both nucleophile as well as the reactant, both are coming. So rate is directly proportional to the alkyl halide as well as nucleophile. So now we can say one thing, as the rate is directly proportional to alkyl halide, so and nucleophile both are having one and one power. So it is a order of the reaction is 2. Order of the reaction is 2. That is why it is
So,
called
okay.
bimolecular. Bimolecular nucleophilic substitution reaction. Bimolecular nucleophilic substitution reaction. Okay, then in that case, now what we have to do? Rate, yes. What could be the reactants that will favor SN2 reaction? What could be the reactants that will favor the SN2 reaction? Okay, so in SN2 we know that this nucleophile is attacking first. So what could be the favorable reactants? In this case, because the nucleophile is attacking from the backside, and when it will feel the steric repulsions, so its tendency to attack from the backside will decrease. So when the carbon is having the smaller groups, or we can say when the carbon is having more number of hydrogens now, in that case the nucleophilic attack will be easy from the backside, right? So we can say
Yes.
here rate is more for 1 degree alkyl halide, 1 degree alkyl halide, 1 degree alkyl halide, then it is for 2 degree alkyl halide, then it is least for 3 degree alkyl halide, right? It is just opposite from SN1 reaction. In SN1 it was highest for 3 degree alkyl halide, then it was for 2 degree alkyl halide, then it was for 1 degree alkyl halide. This was the rate, and this is the rate for SN2. Okay, and it was least in the case of SN1. That means we can say when 1 degree alkyl halide is there, we will prefer SN1. Sorry, we will prefer SN2. When 3 degree alkyl halide is there, we will prefer SN1. Okay. So here, what we can see, if we talk about the stereochemistry in the product. So this nucleophile is attacking from the back side. So the configuration will get reversed. Suppose this was a chiral center. It is not now a chiral center, but suppose this group is A, this is B, this is C, and the Br is D. So you are having 4 different groups. So it is a chiral center. So if the nucleophile is coming from the back side and it was having R configuration, but now the nucleophile is just opposite to the Br, so the priority will order like the 1, 2, 3. The direction will get reversed, and that is why you will be having the configuration as S now. So we can say in the case of SN2, in SN2, inversion in configuration can be seen when inversion in configuration can be seen when chiral center is present. Now, like that is only possible when chiral center is there, right? Once there was a question in the JEE advanced exam. So what they write? They wrote SN2. In SN2 they wrote inversion takes place, but that is not always true. Yeah, that is true when chiral center is there. It is not having a chiral center. So if they say, like suppose this is the reaction, as we know it is SN2 because it is 1 degree carbon, but here the inversion is not happening because this is not a chiral center. Inversion is of configuration, and configuration belongs to a chiral center. If there is no chiral center, how can be the inversion, right? Got it?
Yes, got.
Yes. So if we talk about the SN1, in SN1, what happened about the stereochemistry of the product? This nucleophile is attacking from the above and below. And suppose it was a chiral center. A, B, C is there. Okay, and the nucleophile is coming, which is D. So now it is a chiral center. So nucleophile can attack from the above as well as from the below. So we can say one thing, that you will be getting two products when it is a chiral center. You will be getting two products, and both will be the enantiomers of each other. So here we will be getting a mixture of enantiomers. Okay, and mixture of enantiomer is known as racemic mixture also. So in SN1, racemic mixture or mixture of enantiomers is obtained when carbon is chiral center. And which is this carbon? The carbon which is having leaving group, right? The carbon on which the reaction is happening. If that is a chiral center, so in that case we can say there will be there we will be getting racemic mixture. Okay, so this is about the basic idea about the SN1 and SN2. Like this is how they both are happening in different ways. This is how the mechanism of those will be happening, right? But we have to actually identify the reactions. Like they will give reactant and they will give nucleophile, and they will ask like what will be the product. So we need to know in every case what is the preferred mechanism, right? And how to see that. Okay, so let us see how to see that. In SN1, the nucleophile, you can see better in the rate of the reaction there is no role of nucleophile. So when the leaving group, rate of reaction, rate of SN1 does not depend on the nucleophile,
Yes,
not
okay.
depend on nucleophile, neither its concentration nor its type. Suppose if you take strong nucleophile also, na, then also the rate won't be affecting, because in the rate of reaction there is no role of the nucleophile. And if you suppose you are taking 5 gram nucleophile, and if you take 10 gram nucleophile, like if you increase the concentration, then also we want to be seeing any change in the rate, right? This is what happens in the case of SN1. So generally what happens, nucleophiles are weak or neutral in SN1 reaction. Like these are the keys to identify the reaction as SN1 or SN2. For example, in SN1 you will see the nucleophile as neutral. For example, water. For example, we
Yes,
can take ammonia. For example, we can take this ROH. These are the one which are neutral nucleophile. Those we will be seeing in the case of SN1. Okay. Now SN2. Rate of SN2. You tell me, depends or does not depend? Depend
SN2
on the
depend.
nucleophile. Like it depend both on the concentration, like in the rate nucleophile is coming. So if the nucleophile is stronger, rate will be faster. If the nucleophile concentration is more, then the rate is also more. So we can say rate of SN2 depend on the nucleophile, and nucleophile are strong, or we can say charged in SN2 reaction. In SN2 reaction, we mostly will see the nucleophile as the charged one. For example, we can say the OH minus, we can say the SN minus, SH minus, NH2 minus, etc. Right? These will be the nucleophile in the, or we can say OCS3 minus, alkoxy, OCS3 minus. So these are the nucleophile generally seen in the case of SN2 reaction. Fine. Now what happens? Actually, this is the nucleophile. On the basis of nucleophile, also we have decided. Now the third point I have to talk about is the living group. So you tell me, Hard, that if suppose living group is stronger in the case of SN1, so the rate will be high or less?
It will be faster in SN.
Yes, rate will be faster. And what about SN2?
Slower.
Why slower? Like if the living group
Oh,
is better, then it will be easier for living group to remove, right? Suppose in
oh
the case,
yes.
suppose the
Okay.
same reaction I am taking, the example whatever I have written here, the same example I am taking, but instead of bromine, I am taking fluorine, right? We are taking fluorine. So fluorine will be difficult to remove. So that will be having a slower rate. So both of the cases, in both the cases, when the living group is good, the rate will be faster in both the cases. So this is common for both SN1 and SN2. So we can write better living group increases the rate of SN1 reaction. Same thing here also. Better the living group increases the rate of SN1 reaction. Okay, fine. Now you can see, so we can write rate when iodine is there, rate is faster, bromine is there, slower, chlorine is there, slower, fluorine is there, slower. Same thing will be there for the SN2, iodine, bromine, chlorine, fluorine. Like the rate will be faster when we are having iodine for both of them. So this is the thing which is common for both of the mechanisms. Now we will see the role of solvent. Solvent role is also very important. Solvent will also play significant role to identify the reaction mechanism. Role of solvent. Suppose 3-degree alkyl halide is there, then there is, like, we are sure ki their reaction will be SN1. If the reactant is 1 degree primary alkyl halide, then the reaction will be SN2 because of the less steric crowding. But suppose 2-degree alkyl halide is there, then how will you do that? If 2-degree alkyl halide is there, even if 1 degree, like, how to identify? Because 2 degree both can happen. So now it will depend on the solvent. Or by taking a suitable solvent, actually we can divert our reaction to a to the desired mechanism. Suppose a reactant is there, right? 2-degree alkyl halide is there, and then you want the reaction to go via SN1. So you can take a suitable solvent so that reaction will proceed more via SN1. But if you want SN2, like SN2, then you have to take the solvent which prefers SN2. So now we
Yes.
have to see which solvent prefers which one. In the case of
Okay.
SN1, polar protic solvent. Polar protic solvent prefer SN2, SN1, and in this one, in role of solvent, if we talk about in SN2, then the solvent is polar aprotic. Polar aprotic solvents are there. Okay.
Yes.
And we have seen this. What are polar protic solvent? Like water, like alcohol, like phenol, like acid. So these are what? These are polar protic solvent. If we talk about polar aprotic solvent, so then the example we are having DMF, DMSO, DMF, DMSO, acetone. These examples we are having, and these all are important. Okay, so now what I am doing here is I am writing some reactions. You have to just tell me the preferred mechanism. Okay, preferred mechanism you have to tell. Question is identify the preferred mechanism. Okay, yes, you have to tell me the mechanism in these all cases. Preferred mechanism.
SN1.
SN1, yes.
Second one's also SN1.
SN1 or SN2.
I think SN1, sir.
Why SN? Acha, second one is this one or this one you are talking?
The first one you circled.
This one.
Huh.
No, actually that is a 1 degree, no? 1 degree alkyl halide is there.
Oh,
Although the
yes,
solvent is
SN2.
water,
Okay.
but in 1
Yes,
degree it is very difficult to perform
SN2.
SN1. So SN2 will
Yes.
happen. Next,
DMSO will do SN2.
SN2.
SN1.
SN1, yes.
DMF will also SN2.
SN2.
SN1.
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 Then also SN1. Yes. I repeated the question. So I was saying this question. Now,
SN2.
yes. Okay. So we can guess the product also. Like, can you tell me where you will be getting one product? In this case, you will be getting one product or two products.
Oh, we can say 2, right? Wedge dash. No,
But
it's not fair.
yeah, it will be one
Doesn't
only.
matter. One.
Yes, one only. Only one product will be getting. In the next one,
One product only.
one product only. Like the configuration is not.
Sir, that will remain BR or OH? We wrote BR in the
Oh,
first
yes.
one.
That will be OH. Yes, that will be OH. Okay, in the next one. Next one also
OH. No. CH3.
one product. Yes, and in the next one
OH.
OH,
OH.
OH,
OH.
OH, and again OH. Yes, in all the cases, the one products are obtained. In none of the case, the inversion is happening, and in none of the case, racemic mixture is obtained. Although they are SN1 and SN2, but that is true when chiral center is present, right?
Yes.
Yes. Okay. So now we have the right idea about when the SN1 and SN2 will happen. So, okay. Now we can solve some questions. Yes, I wanted to mention this thing specifically. Rate of SN1 is directly proportional to stability of carbocation. Stability of carbocation. Like when the living group removes, because that is the slowest step. Okay. So carbocation is forming is the slowest step. So if the carbocation is stable, rate of the reaction will be faster. And when the carbocation is less stable, rate of the reaction will be slower. So this is rate, about rate. Okay. Now the rate of SN1, actually sometimes they ask about rate of hydrolysis. So rate of hydrolysis also depends on this thing, like the stability of carbocation, because the hydrolysis also happens via SN1 mechanism, via SN1 only. So now you have to solve this question.
Okay.
Okay, done.
Yes, I think so. I'm getting 3124.
Okay, so what we will be doing, we will be checking the stability of carbocation, right? So carbocation will be more stable in the case of 3, because it will be getting resonance from 2 benzene ring. Then it will be 4, and then among 2 and 1, this is a 3 degree. and
So
it is
4,
having,
but 4 is having 2 hydrogen, not 3 degree.
but like resonance is dominating, no? Resonance is dominating.
Oh, oh, then be option A. Okay.
Yes, option A will be the right answer. Okay, now I'll be telling you the very important thing, that some cases are there where both SN1 and SN2 can happen, and some cases are there where both SN1 and SN2 cannot happen. Okay, so question, we can take it as a question. Why nucleophilic substitution are less possible or not possible on aryl halide or vinyl halide? Yes, so we can take the benzene ring, and then we can take the halogen. Yes, so here we can see, suppose this is a benzene. Okay, that is aryl halide. When halogen is attached to the benzene ring, that is aryl halide. And what is vinyl halide? CH2 double bond CH and that X. That is called vinyl halide. Okay, so aryl and vinyl halide, why the substitution cannot happen? See, the nucleophile will be attacking, and this species itself is electron rich. This is electron rich because the benzene is electron rich, that acts as a nucleophile, and this particular living group, that is also having the lone pair of electron. And first thing is that electron rich. Second thing is that this lone pair is involved in the resonance. So if the lone pair is involved in the resonance, then there are double bond characters here, and due to the double bond characters, this bond is strong. Carbon living group bond, it's stronger due to resonance. So difficult to break. So it is difficult to break. Third thing is that this uh, third thing is that this living group is attached to the sp2 hybrid carbon. That carbon is sp2 hybridized. So sp2 carbon and then living group, that bond is also like stronger than sp3 carbon living group bond. Actually, when the S character increases, the bond strength also increases. So because of these three reasons, the nucleophilic substitution is difficult on the aryl halide. Similarly, here also, in this case also, the same thing. Nucleophilic substitution won't happen because of the same reasons. This is having resonance, and that is sp2 carbon, and those are also kind of nucleophile. So because of these
Yes,
reasons, the reaction won't happen. Now you tell me one thing. Suppose if we talk about the bridgehead carbon and then we put the living group here, so the reaction SN1 or SN2 can occur on the center or not? SN1 or SN2?
SN, it won't do, right? It's bridged.
Yeah, it is bridgehead carbon. So when the SN1 happens, so the formation of carbocation takes place, right? So if you remove that, then the carbocation which is forming is highly unstable because of the bridgehead position. So because of that, the SN1 won't happen. Then if we talk about SN2, so because the carbon is 3 degree carbon, so on the 3 degree SN2 is not allowed. On the 3 degree SN2 is not allowed, right? So because
Yes.
of these reasons. Okay, so these are the compounds on which both SN1 and SN2 are not allowed. But we will see some compounds or some reactants on which both can happen nicely. Reactants on which both SN1 and SN2 can occur. Let us see. Okay. So what are those reactants? First reactant is aryl halide. This is benzene. This is CH2. This is X. This is CH2 double bond CH. This is X. Sorry, not this one. This one. CH2X. On the benzene, if the next carbon is CH2, so that is called benzyl group, and halogen is there, so benzyl halide. Okay. On the alkene, C double bond C, if the next carbon is CH2, then that is called allyl. So allylic halide. Allylic position we can say. Allylic carbon, right?
Allylic carbon. Yes.
So the reaction, both reaction are feasible on this center beta. Why? Because that is firstly it is 1 degree. So when it is 1 degree, so SN2 to can happen very easily, right?
Yes.
And when if you talk about the SN1, so SN1 can happen when the forming carbocation is stable, and you can see on the benzene if you make the CH2, so that is stable because of the resonance.
Yes.
Right, so both can happen. Similarly here also, as this is 1 degree, so SN2 can happen. And if we talk about the SN1, then the forming carbocation is stable because of resonance, so that is why SN1 can also happen. But sir, how, which one will happen? So it will depend on the now the nucleophiles as well as the solvent. Suppose if the solvent is polar aprotic, we will favor more SN2, right? And when it is polar
Yes.
protic, then we will favor more SN1. Got it, no?
Got it.
Okay. So I am giving you one question. You have to give me the product. You have to tell me the product. This is benzene, CH2, CH2Br, and this is Br. And what we have taken? We have taken NaOH, aqueous NaOH. So what will be the product? Okay, so where the nucleophilic substitution will happen? On which Br? On like which Br will be substituted? Beta, on this part, like if this Br to cannot be removed because that is
Yes.
directly connected with benzene. But here,
Yes.
this Br can be removed, like it can be
Yes.
removed by both the mechanisms.
OH.
So yes, we have to do the substitution here only,
SN2. Yes.
SN2, because the nucleophile is stronger, so SN2. But that Br will be as it is. That Br won't be changing.
Okay.
So CH2 OH. So that the leaving group, when it is directly attached to the benzene ring, no? When leaving group is directly attached to benzene ring, then we do not have to do the substitution on that center, right?
Okay.
Now, almost covered. One last thing, rate of SN1 is directly proportional to stability of carbocation. This thing I have told many times, but directly proportional to, we can say, electron donating group also. If we talk about rate of SN2, that I haven't told. Rate of SN2. Like suppose, first thing, like we will see that SN2 will happen more in the case of 1 degree alkyl halide, then 2 degree, then 3 degree. But suppose two cases are there, both are 2 degree, then how will you compare? So we can say, in the case of SN2, mechanism you see. In the case of SN2, if we see the mechanism, that's the mechanism. This one, right?
Yes.
So this carbon, this particular carbon is having this carbon is having more electron density because the leaving group and the OH both are connected with this carbon. Like it has made 3 bonds, but it has more electron density around the carbon. So the group which are able to withdraw the electron density, like the withdrawing groups are there, then it becomes easy for carbon
Yes.
uh, to come in the transition state or to come in the lower energy transition state. Okay, the graph looks like that. Okay, so if when electron withdrawing groups are there, then it looks like that. Okay, so because of
Yes.
electron withdrawing group, the transition state will become lower in energy because that will become more stabilized. Because this carbon high electron density, if you are having some electron withdrawing group, the high electron density will be compensated or it will get stabilized. So in the case of SN2, we can say the rate is directly proportional to, inversely proportional to, first thing is steric crowding. That matters the most, steric crowding, and directly proportional to electron withdrawing group. Yes. So now what we are going to do, we are going to do last thing. In the case of SN1, SN2, we are going to compare the rate. For first for SN1, then for SN2. Compare rate of SN1 reaction. Compare rate for SN1 reaction. Okay. I am giving here some questions.
Okay.
This is A, B, C, D, E. Second, PHCH2Cl. Third is this one. The fourth is this one. Yes, so SN1 rate you have to tell me.
So here neither SN1 nor SN2, right? For the first one.
Yes, so first will be slowest. In the first, rate will be slowest.
Yes. E will be the highest.
No, E will not be the highest.
No? Okay. Oh wait. So okay.
Okay, let us see. In the first one, you can see in the A case, the leaving group is directly connected to benzene ring. So, like it will be the slowest, it will be difficult to remove Cl from here. So, it will be least. Then other cases, you can see all are B, C, D are benzylic halide. So benzylic halide, the carbocation forms. What we have to do, we have to just compare the stability of forming carbocation. So the carbocation will become stable because of resonance. But here there is no resonance. And resonance is more stabilizing, right? So
Yes.
E will be less. Now BCD. In BCD, B will be highest. Then there will be C, then there will be D. This will be the order.
Okay.
Okay, so if we talk about the second one,
A highest, then B, then C.
yes, in the case of A, there will be dancing resonance.
Yes.
Because of that, that carbocation is highly stable, even more than the resonance.
Yes.
Okay, in the third one,
A C will be the least.
C will be least. Then we have to see the stability of carbocation. Let us put methyl here.
Or D then? B?
B and then A.
Yes.
Yes. In the fourth one,
This will be based on ease of leaving. So, higher the mass, easier it will leave.
hmm.
So, C is the least. Uh,
Hmm.
uh, between A.
Yes. So that will be the orders for SN1. Okay. Now let us do the same thing for SN2. You have to tell here
E will have the highest state.
it is SN2.
Oh, my bad. Okay, so A will have the highest state.
A will have the highest. Okay.
C,
C,
B,
B,
D, E.
D, E. Right. Correct. And how the A is coming the highest one?
Also, resonance.
Where the resonance will happen? Like you will not be
Will
having a
go.
carbocation here.
Hmm?
In the case of SN2, we do not make the carbocation.
Uh, no, like it's more bulky, right? So
No, no, beta. Actually, the thing is, in the case of SN2, I told you the when the electron withdrawing groups are there, then they will withdraw the electron density from the carbon and they will stabilize the transition state. So this C double bond O is electron withdrawing group.
yes,
So because of that, it will stable the transition state. That is why it is highest. First, we are having 2 degree and 3 degree. So we will taking these in the last, and then we are all are having 1 degree, 1 degree, and one
one.
degree. So among these, we can see the electron withdrawing group. So A will be highest. Now in B and C, how we'll compare? So in the case of C, there is no resonance at all. Like pH is not having resonance with carbon. But again, this pH carbon is sp2 carbon, and sp2 carbon has electron withdrawing effect. sp2 carbon is having minus I effect. So that is why it will again stabilize the transition state. Rather, this is having CS3, which is having plus I effect. So which is more stable? C is more stable. Like in the case of C, transition state is more stable. Because of that, we can see the rate will be like that. Okay, C is higher than B. Got it?
Got.
Yes. So how the graph is there? The last thing we can see the graph. You have to tell me which graph belong to SN1 and which belong to SN2. I'm making the graphs. Or we can say energy profile diagram. Energy reaction coordinate.
SN1.
Yes, that belong to SN1 and this belong to SN2. Transition state, reactant, product, product, reactant, intermediate. That is transition state 1. This is transition state 2. Yes. Okay. So this is SN1 and that is SN2. And of course, in the case of SN1, as we can see, the carbocation is formed. So carbocation can show the rearrangement also. If that is possible, we will be doing rearrangement also.